All right, so what we're going to do is we're going to figure out from this piece of information. I had to stop. I had to talk to someone for a second. How to calculate the wavelength. So if we're looking at the graph, which one is the valence electron? And that should be this one. Because remember, this is the outermost. Because if we look, 1s2, 2s2, it's the same height. But if we went from right to left, this would be 1s2, and this can no way be 1s2. So that's why the outer peak again, that's why the one I circled is our outer shell. So we're going to use this piece of information right here. So that's representing our energy, because again, this is our energy in joules. So we would do 0.980 times 10 to the negative 18th equals, all right, h, which is Planck's constant, and then c is the speed of light, so its constants are given to you, over the wavelength. So remember, these are constants. 6.626 times 10 to the negative 34th, and this is 2.998 times 10 to the 8th. So then pretty much, since you're solving for something on the bottom, you're just doing this and putting this, our energy, on the bottom and divide to find your wavelength. So our wavelength should come out to be roughly 2.03. And you might not get the same answer I did, because when I did this, I used 3.0 times 10 to the 8th, so it might not make a big difference. Or you might not be as exact as this, but it's fine. All right, so the second part, I already worked it out. There you go. All right, so in the upper atmosphere, ozone molecules decompose as they absorb ultraviolet radiation, as shown in the equation below. Oops, sorry, I read too early. How much energy in joules does the ozone molecule absorb per photon? So here, now we have hertz. So remember, hertz is frequency. And we have this, 387 kilojoules per mole. So remember, this can be a conversion factor. So remember, this is written as 387 kilojoules per 1 mole. So what we're going to do is, remember, 1 mole of anything is always going to be, so this is a mole of bonds. So remember, 1 mole of anything is Avogadro's number. Because our goal is to convert to joules, but we can't do that because there's kilojoules per mole. So that's why I'm using Avogadro's number. So then from there, you should get 6.43 times 10 to the negative 19th joules. So now, is this enough to break? Is this enough energy to break the bond in the previous? Sorry, I'm scratching my back. In the previous problem. So if we look at our other answer. Oh, I'm sorry. Hang on, I didn't work it out. I was looking at the other problem. So if we're trying to figure out how much energy, I totally skipped that. I'm so sorry. This was the other problem I was talking about, and I didn't even work it out. All right, so here we can use, since we'll only be given frequency, we can just use HV. So remember, H is Planck's constant. V is 1.0 times 10 to the 15th. So our energy should be 6.626 times 10 to the negative 19th joules. All right, so from there, now compare the numbers. I'm going to compare this number to this number. Since this is our energy for ozone, this is the minimum energy required to break it. Based on the top part, we do have enough energy, since our answer here is higher. Sorry, I'm trying to get my laser out. Since our answer here is higher than the answer down here, we have enough energy to break, because this is how much we need to break the bond. So if you have 1 times 10 to the 15th hertz, that photon with the frequency, which is this much energy, it can break this bond. So the answer